Well, here we are. We've survived verifying, and we're ready for a new challenge. Unit 4 basically encompasses two big ideas. Just like the last unit was all about verifying identities and solving trig equations, this unit, Unit 4, is about trigonometric formulas and using them, and then trigonometric inverse functions and kind of understanding how they work and what their limits are. But for right now, we're going to jump right in with the formulas. And the first formulas are the sum and difference formulas. We have sum and difference formulas for sine, cosine, secant, cosecant, tangent, and cotangent. Although we're really only going to do sine, cosine, and tangent. You can get the others by just simply taking the reciprocals of those three. One important idea that I just want to review with you, if you will, going back to Algebra 1, is this idea right here. If I have 2 points on a coordinate plane, how can I find the distance between them? How can I find that distance? If they're directly horizontal, we can just count the distance or subtract. If they're directly vertical, we can do the same thing. But when they're diagonally across from each other, it's not quite so easy. But it's actually not that hard either. All right? So how can we find the distance between these 2 points? The key comes down to something we learned a long time ago, right triangles. If we build a right triangle, making the distance we're trying to find the hypotenuse, we can pretty easily find the legs of the right triangle by simple subtraction. Okay? If point 1 is x1, y1, and point 2 is x2, y2, this point right here, point 3, would have the same x value as point 2, and it would have the same height, the same y value as point 1. And so we now can pretty easily determine that A is going to be x1 subtract x2 or x2 subtract x1. It doesn't matter as long as you take the absolute value. That distance will be consistent, and the B value is going to be the same idea, y2 minus y1. And if we put those into the Pythagorean theorem, we can go ahead and apply that and find the distance. That's the idea behind the distance formula. Here's a little bit of a prettier picture of what we're dealing with. But once again, so just a prettier picture here of the situation we were just talking about, where here's your distance, your horizontal distance, x2 minus x1. Once again, you can do x1 minus x2. A lot of textbooks have that. We're going to end up putting it into the Pythagorean formula. We're going to square it, so it's going to become positive anyway. Y1 minus y2, we square the two legs. We take the square root of that value so that we can, get d squared down to d, and that is the distance formula. Why are we going to use this? Well, maybe it's going to be a surprise, but let's just remember this formula, the distance formula, to find the distance between 2 points on the coordinate plane, and we're going to pull that out of our hat in just a couple minutes. Okay? Here's a couple pictures though first. All right? The first picture is going to be a picture of a rotation, but it's going to be a rotation unlike other rotations that we've done before. Usually we just do a rotation and that's it. And the distance of the rotation, the amount of rotation, is from the x-axis, positive x-axis, the standard position, to the terminal side. Well, this is going to be a little different. We're going to do two rotations. We're going to do an alpha rotation and a beta rotation. The alpha rotation will be greater than the beta rotation, and we are going to then subtract the rotation. So here we go. The red ray, the red spoke, the red radius is the that we're calling point 2, okay, is our alpha rotation. And as you can see right here, it's labeled alpha, getting us to that point. We're calling it point 2. Well, we're just going to call it x2, y2. Now, a smaller rotation right here, this blue spoke, this blue radius is beta, and that's getting us over to point 1, which we're calling x1, y1. The difference between them, and so this is what we're really talking about right here, guys. This is the angle, all right? This is the angle alpha minus beta. This is this pink rotation right here, alpha minus beta. That's the value that we're interested in finding, the value of that ratio, which can be pretty tricky if we left it in this current position. And so what we want to do is we want to do something, we want to make a little shift is what we want to do. Now, I'm going to tell you ahead of time that this shift is going to lead to something fairly ugly, something, in fact, that you might even describe as hideous. So let's take a look at picture 2, alpha minus beta rotated into standard position, and just see how bad it is. Oh my gosh, I told you, it's awful. Oh, I can't handle that. Get that out of my face. Come on. Out. Move. Leave. Thank you. Oh, that was horrifying. Actually, that wasn't the ugly part at all. I was just kidding there. This rotation is really not that bad. This is where we were. Oh, he came back. Get away, dude. It's like he never goes away. We're going to rotate this just like that. We're going to rotate it into the standard position. Why? Well, for one thing, it gives us a point that we know a lot about, because the x-axis point 1, 0, we can now use as one of our points. Now, the other point on this rotation, point 3 we're calling it, we can't do much with that. All right? We're just going to have to call it x3, y3, and leave it at that. But the rotation itself, though, is exactly the same. We have alpha minus beta here, alpha minus beta here. They are the same rotation, and we're going to use these two pictures to build the formula that we're after today. All right. Notice that these two rotations have created two distances. The distances between point 1 and point 2, which we'll call distance 1, and the distance between point 3 and then the point 1, 0, which we'll call distance 2. Can anybody guess why we were reviewing the distance formula now? That is correct, because we are going to use that formula with these points to create some equations. Here's something we want to know ahead of time, though. These two triangles that we created, okay, is there anything we can determine about these two triangles? Anything special? Anything significant? If I told you to think back to geometry, I gave you a couple seconds, you might start thinking about things like, oh, I don't know, SSS, and SAS, and ASA, and so on and so on. Actually, the other one is AAS. These are the geometry triangle congruence postulates and theorems that you learned back in the day. And sure enough, we have one of these at our disposal right now. And if you notice that these two sides are congruent to these two sides, and look, alpha minus beta is the angle between those two sides, sometimes called the included side. We have side angle side. And so by the side angle side postulate, we can prove that these two triangles are congruent to each other, meaning identical. Now, there's another little something from geometry. It's not really a theorem or a postulate. It's really based on the definition of congruent figures, but we called it CPCTC, which stood for corresponding parts of congruent triangles are congruent. And so because the corresponding parts of these two triangles must be congruent, and because these two sides correspond to each other, we know that the side which is D1 is congruent to the side which is D2, and of course by the definition of congruent sides, that means their lengths must have the same distance. And so D1 is equal to D2. This is where we finally get to start our little algebraic celebration. So let's watch this. Remember when I told you things were going to get ugly, and you thought it was only going to get as bad as Keanu Reeves? And hey, don't get me wrong, Keanu Reeves is not pretty, but this algebra is a little bit crazier. It's really, I mean, it's not terribly freaky. It's just a lot of parts. So here we go. Distance 1 is equal to distance 2. We know that distance 1 is x1 minus x2. Actually, we did x2 minus x1 squared plus y2 minus y1 squared, and we take the square root of that. Distance 2, y3 minus 1 quantity squared plus y3 minus 0 quantity squared. That's this distance. And just to be clear, the distance 1 is that distance. We know that those are equal, so we're going to go ahead and set those formulas equal to each other, just about like that. All right? Now, nobody likes a bunch of square root signs, but here's the beautiful thing. Each side of this has a square root sign, so why don't we just square both sides? Square both sides of this equation, and we'll make those square root signs go away. That makes everybody happy. At least happier, right? Now, the happiness doesn't last very long, because now what we have to do is we have to go to our binomials in here, like this guy right here, and this guy right here, and this guy right here. And we don't really worry about this guy right here because it's just going to turn into a y3. But these other three guys are going to have to be expanded. You can't just do the first term minus the second term squared. That's not how algebra works. You have to square the entire binomial, so you end up having to FOIL it out. You have to distribute it. And so what we end up with is this fantastic bit of expression right here. X squared, well, let's just do the first one. x2 times x2 is x2 squared. The last term in that would be y1, negative y1 times negative y1, which would still be positive y1 squared. And then in the middle, we'd have a negative x1, x2, and another negative x1, x2. And that's where this guy comes from right here, is putting those together. This is just kind of a formula for squaring a binomial that you probably learned as far back as Algebra 1. But that's where that guy goes. And we square this guy, and we get these three terms, right? And then on the other side of the equation, we square this guy, and we get these three terms. And then finally, y3 squared is just y3 squared. So that one's the only one that's not too bad. It's pretty ugly. I agree. We don't like it very much, but that's where we are right now. We're going to make one little move here, and it's really an organizational move. I'm going to move the x2 squared and the y2 squared together, the x1 squared and the y1 squared together. On the other side, the x3 squared and the y3 squared together. Why? Why would I be making this move? Well, you also might be asking, how does this have anything to do with trigonometry? I see no sines, cosines, tangents, any trig functions. We're going to answer both of those questions simultaneously right here. Why did we move these dudes right here together? And where are those trig functions? Let's find out what we're going to do. Remember from Unit 1, when we were building all of our trig identities, when we were building the unit circle, remember that we discovered that in the unit circle, y is equivalent to the sine of theta. The sine of theta is just the ratio of y. Technically, it was y over 1, opposite over hypotenuse, where the hypotenuse was 1, and the opposite side was the vertical leg of the triangle. Likewise, cosine is x. You guys know these pretty well. Well, if we use these two identities, these two relationships to our advantage, we can rewrite all of the x's in terms of cosine, and we can likewise rewrite all of the y's in terms of sine. X1, remember, X1, Y1, the point P1 was based on beta, so we use that rotation of beta. X2, Y2 was based on alpha, and X3, Y3 was based on both. Remember, that was when we shifted it back to the origin here, and so our rotation was actually alpha minus beta, which, just to bring you back to the beginning, is the same. Yes, that's not going to work, is it? It's the same as dot rotation right there. Okay. We're gonna do a whole bunch of substitutions there, guys. We're gonna do a whole bunch of substitutions. This is where we left off. This is where our last step was algebraically, and what we're gonna do now is we're gonna replace all the x's and y's with sines and cosines. La la! Isn't that gorgeous? Well, okay, maybe not, but it's gonna get better, because you can start to see why we put those x's and y's together of the same point, because that gave us cosines and sines of the same angle. And we all remember what cosine squared plus sine squared of the same angle is, don't we? Don't we all remember? I believe it's 1. The Pythagorean identity helping us again. It helped us a ton in our verifying phase. Now it's coming back to pay even more dividends with this derivation. Cosine squared of beta plus sine squared of beta, 1. Okay, these guys right here, not much you can really do there. All right, we'll have to leave that alone for now. Here's another one though. Even though alpha minus beta is not a pretty angle, it's the same angle, so cosine squared plus sine squared is still 1. And then finally, last but not least, we've got the 2 cosine alpha minus beta, which there's not much we can do with right now. So let's simplify a little bit. 1 plus 1 is 2. On the other side, we also have a 1 plus 1 is 2. We can, I believe, just subtract those 2's off, can't we? Subtract those 2's off. That leaves me with negative cosine alpha cosine beta minus sine alpha sine beta is equal to negative 2 cosine alpha minus beta. There's a lot of 2's in there. Why don't we just factor the 2 out on the left side of the equation there, and then divide that negative 2 right out of the equation. Look at that. Dividing that negative 2 out leaves us with this right here. And I know you're probably by this time saying, where is this going? And the answer is right here. This is where it's going. This is the answer. The cosine of alpha subtract beta. This is a difference formula for cosine. The cosine of angle alpha subtract angle beta is cosine alpha cosine beta plus sine alpha sine beta. Okay, so you can find this new angle that we know nothing about, alpha minus beta, by just using what we know about alpha and what we know about beta, which is going to help us in a couple different ways. So I don't know, I'm pretty happy with that. I think you deserve a hand, huh? Now, where do we go from there? Well, we're going to go some other places really quickly. Now that we know that cosine of alpha subtract beta is cosine alpha cosine beta plus sine alpha sine beta, we can get a little tricky here and rewrite cosine of alpha plus beta, which we don't know yet. We don't know this formula yet, right? But I do know the difference formula, so I'm going to rewrite the addition as a difference. Look at that. Okay, now I can just go ahead and plug alpha and negative beta into this formula now. I can just apply this formula exactly. And so we're going to go ahead and do that. It's going to be cosine alpha, cosine negative beta, plus sine alpha, sine negative beta. And before you start freaking out about those negative angles, remember those even odd identities. We learned to deal with those negative angles. The cosine of negative beta is just a cosine of beta because it's an even symmetric function. And the sine of negative beta is the opposite of the sine of beta, so negative sine beta, which is just going to give us something very similar to what we got before. Cosine alpha, cosine beta, subtract sine alpha, sine beta. Okay, so here is just that quickly the sum formula for cosine. We can quickly move into the sine formulas now. We have to use a slightly different trick this time. What we're going to do is we're going to use, well, what's the relationship between sine and cosine? Oh yeah, they're co-functions of each other. Sine and cosine give equal ratios at complementary angles. Very cool. And so what is the complement of alpha plus beta? Well, assuming it's less than or equal to 90 degrees, it would be pi over 2 minus alpha plus beta. Subtract alpha plus beta. Those would be the complements of each other. Okay? And so now I'm going to do just a little bit more trickery. I'm going to rearrange the inside of that parenthesis. I'm going to distribute the negative sign. So we get negative alpha, negative beta. And then I'm going to put the pi over 2, I'm going to group that with the alpha. So instead of grouping alpha and beta together, I'm going to group the pi over 2 with the alpha and leave the beta alone. I now have two different angles. I now have pi over 2 minus alpha as one angle, and beta as the other angle. Okay? So let's go ahead and plug them in our formula now. Let's plug them in the formula. This guy right here, remember, this is the one we came up with to begin with. We're going to use that formula right now. And we're going to put these two angles in for alpha. And we're going to put beta in for beta. Okay? And how did we deal with complementary angles back in Unit 1? Oh yeah, cofunctions. The cosine of the complement of an angle is equal to the sine of the complement, and the sine is equal to the cosine of the complement. And so I can turn cosine of pi over 2 minus alpha, cosine of the complement of alpha, into just the sine of alpha. Likewise, I can turn the sine of the complement of alpha into just the cosine of alpha. It's a similar formula, but instead of cosine, cosine, sine, sine, like with the cosine formulas, we get sine, cosine, cosine, sine. And this is our sum formula for the sine ratio, sine of alpha plus beta. Now that we have that going, now we see how that little trick kind of works itself through, we can just go back and we can do the exact same little dance with the sine of alpha subtract beta. The only difference is going to be this time I'm going to have to use the sum formula for cosine. And so we end up with a subtraction of our two terms. And this is the fourth formula we come up with, the sine of alpha subtract beta. Okay? So after we got that really, really nasty one, the cosine alpha minus beta, these next three actually come about fairly quickly if you know how to set them up. Finally, let's just take a quick look at tangent of alpha plus beta. That looks nasty until we realize that isn't tangent sine over cosine? Yeah, it's the fundamental identity. Tangent is sine over cosine. And we already have a formula for sine, and we already have a formula for cosine of alpha plus beta. We just came up with those formulas. And those formulas were, for sine of alpha plus beta, sine alpha cosine beta plus cosine alpha sine beta. And for cosine alpha plus beta, cosine alpha cosine beta subtract sine alpha sine beta. What are we going to do now? Because that is kind of ugly, isn't it? Well, what we're going to do is we're going to take this guy and we are going to multiply through by 1 over cosine alpha cosine beta. It's just a little algebra trick. Don't be frustrated if you have no idea where it comes from. It's just, it's really more based on this term than anything because it's the exact reciprocal of this term. But we're going to multiply through by this fraction, and we're going to see, we're going to see some cancellation and combination as we go. So this is what we get right off the bat, and then we can split those. We can split those terms so that we have two fractions on top, two fractions on the bottom. And then we can start to see what's going to stick around and what's going to go away. Like these cosine betas right here, see you later, right? These cosine alphas right here, adios. These guys both cancel, but we kind of knew that was going to happen with that term. We knew that was the reciprocal even from up here. And then over here, nothing's canceling. This last term, we don't seem to have anything going away. So what do we have left? Well, we have this. This is what we have. The nice thing, though, is that sine alpha, cosine alpha is just what? Oh, it's tangent alpha. And sine beta over cosine beta, oh, that's just tangent beta. Nice. And so we just basically turn the remaining functions into tangents. And that gets us our tangent formula. All right. Exactly. I'm not going to make you go through the tangent difference formula, but it's basically the same story, except we're going to use the difference formulas for sine and cosine, and the only thing that changes is the signs of the formula. So we're going to get a subtraction in the numerator and an addition in the denominator. Notice the rest of the formula is identical with the terms that you see. So here we go. These are the 6 formulas for sum and difference. Cosine sum, cosine difference, sine sum, sine difference, tangent sum, tangent difference. And like I said, we're not going to do the cosecants and the secants and the cotangents because we can just take the reciprocals of these formulas and get those other functions. Let's go ahead and break down some examples now. Because right now you're like, okay, these formulas are ugly. Getting them was ugly. I don't even know where you're going to use them yet. Well, this first problem kind of illustrates where we could use them, okay? Cosine 75. If I said, what is the cosine of 75? What ratio is the cosine of 75 degrees? You'd probably reach for the calculator. But what if I said, I'm sorry, but you're not going to be able to use your calculator to come up with this? Well, now we're stuck because we do know some exact values from around our unit circle, but I'm pretty sure 75 degrees is not one. But if we think about those unit circle values, like 30 degrees, like 45 degrees, like 60 degrees, maybe we can build 75 degrees. Maybe that's something that we can create. For example, how about 30 plus 45? Isn't that 75? And that's exactly how these problems work. We use known angles all the way around the unit circle to create angles that we don't know. And so we're going to rewrite this as the cosine of 45 degrees plus 30. If you want to do 30 plus 45, no problem. It doesn't matter. You're still going to get the same answer. A lot of these you can get in different ways. You could add them to get them. You could subtract to get them. For example, 120 degrees is a reference angle in quadrant 2. 45 we already know is a reference angle. We could do 120 subtract 45 and get the same answer using a difference formula. Okay. Now I included the formula up here just so that we could go ahead and basically just start plugging in what we know. Basically we're using 45 degrees as alpha, and we're using 30 degrees as beta. Okay. So let's do that. Cosine alpha, cosine beta. I can already tell this is not going to fit, so you know what? I'm going to slide it down over here. And we're going to subtract the sine of alpha, which we're calling 45 degrees, and the sine of beta, which we're calling 30 degrees. Okay? Look them up on your table, guys. Look them up. all of these are ratios off of the unit circle table of values. Cosine of 45 is root 2 over 2. Cosine of 30 degrees is root 3 over 2. The sine of 45 degrees, like the cosine of 45 degrees, is also root 2 over 2. And finally, the sine of 30 degrees is one of our favorites. It is 1/2. What you're going to find with these problems, you're always going to have built-in common denominators. So that's kind of nice. 2 times 2 is 4 on either side of this. So we're going to get a built-in common denominator of 4. Root 2 times root 3. You are allowed algebraically to multiply a root by a root. The product is a root, so we're going to get root 6. Subtract 1 times root 2 is root 2. You can multiply roots. You can even divide roots. You cannot add or subtract roots. So please, please, please do yourself a favor and don't tell me that root 6 minus root 2 is root 4. That's just not true. If you're ever wondering about those, like on an ACT or something, and you can't remember if it's true, make up a real simple example. For example, what is root 25 subtract root 16? Well, we know that 5 subtract 4 is just 1. And so we know the answer to this problem is actually 1. But if you used the formula that does not work, you would get 3. There's no way that 3 is equal to 1. You cannot algebraically add or subtract roots. So keep that in mind. What does that mean for us, though? Well, that's as far as we can simplify this guy. That is your answer. You're done. Root 6 subtract root 2. Let's take a look at another example. Cosine of pi over 12. Well, we know pi over 6s and pi over 4s and pi over 3s, but we don't know no pi over 12s, do we? So let's look at some radian angles that we know around the unit circle, like pi over 6, pi over 4, pi over 3. If we don't need these right now, but if we kept going, we'd get usually you put the zeros or the 90s in. We're not going to use zeros or pi over 2 reference angles because those are just never necessary in these types of problems. The angles, if we could use those, would already be on the unit circle. So you can just kind of skip to 2 pi over 3, and then we get 3 pi over 4. And then we get 5 pi over 6, and then after pi we get 7 pi over 6. So these are a bunch of ratios, angles, I should say. I'm sorry, that we know are on the unit circle. But it's hard to compare them to pi over 12s because they don't have a common denominator. So all I'm going to do here is I'm just going to go through and convert them into a denominator of 12. So pi over 6 becomes 2 pi over 12, and we're going to get 3 pi over 12, and we're going to get 4 pi over 12, and we're going to get 8 pi over 12, and we're going to get 9 pi over 12, and 10 pi over 12. Wow, that was really bad. And finally, it looks like 14 pi over 12. Now that we have a common denominator, it starts to become easier to determine what values might create a pi over 12 for us. And I think in this case, it's going to be wow, random stuff popping up on our screen. That's kind of weird, isn't it? Let's make it go away. Thank you. So just taking a glance here, it looks to me like we could just probably simply do 3 pi over 12, subtract 2 pi over 12. I mean, there's definitely other ways to do it. 4 pi over 12, subtract 3 pi over 12, 10 pi over 12, subtract 9 pi over 12. But why not just stick with the easiest possible answers, okay? So cosine 3 pi over 12 is pi over 4. and it subtracts 2 pi over 12, which is pi over 6. All right, and now we can use what we have right here, the cosine difference formula. So that's going to be cosine of the first angle, which is generally called alpha, cosine of the second angle, which would be pi over 6, subtract sine of the first angle, the alpha, times the sine of the second angle, the beta. And once again, once you get to this point, it's just substitution game. And in this case, our substitution is going to include the same ratios we're just using before with, root 2 over 2, a root 3 over 2, another root 2 over 2, and then finally a 1/2. It looks like we're going to end up with root 6, subtract root 2 over 4. So many of your answers in this section, so many of them are going to have the same fundamental look to them, simply because the ratios we keep plugging in are all the same. And you know what? I apologize. I'm looking, and I know that this is supposed to be addition. We're using the difference formula this time, not the sum formula. I apologize for that. Hope that doesn't throw you off too much. But you can see that this answer, root 6 plus root 2 over 4, is very similar to our previous answer, root 6 subtract root 2 over 4. A lot of these answers are going to look very, very much alike. Sine 17 pi over 12. I kept that last list, and I'm just going to pull it back over for us here, so we don't have to rewrite all of these. Eventually you get used to them, and you probably don't even have to write them down. But I think what we can do here is do a sine 17, How about 8 plus 9? 8 pi over 12 plus 9 pi over 12 is 17 pi over 12. So I'm going to do the sine of, what would that be, 3 pi over 4 for 9 pi over 12 plus 2 pi over 3 for 8 pi over 12. I think that'll work for us. And now the formula for sine, and we are using the sum formula here, so we're going to use this one right here. And that's going to be sine alpha cosine beta plus cosine alpha sine beta. And our alpha was just what we're using here is 3 pi over 4, and our beta 2 pi over 3. Now, guys, this is really no harder than the previous problems, but you're going to have to be a lot more careful, because in the last two problems, we were always in quadrant 1. And one of the biggest mistakes in these problems, I'm going to repeat this, one of the biggest mistakes in these problems is people forgetting to make sure you're in a quadrant and asking yourself, are we positive or negative in that quadrant? 3 pi over 4 and 2 pi over 3 are both in quadrant 2. They're both in quadrant 2. Okay? Sine is positive in quadrant 2. All right? Sine is positive in quadrant 2. Cosine, not so much. Cosine is negative in quadrant 2. Cosine is negative in quadrant 2. So you look them up on your table, but you must pay attention to what quadrant you're in. Don't just write this and then suddenly change this into a pi over 4 and a pi over 3. You can't do that. These don't add up to 17 pi over 12. You can't just use reference angles without paying attention to what quadrant you're in. So I really, really urge you to be careful about that. This answer is negative root 2. Plus a negative root 6, we'll just call that negative root 6 minus root 6. Subtract root 6. This smartboard hates writing 6s, I've noticed that. I have to go really slow. All over 4. And once again, very similar to the last couple answers, but that's how these problems work out. One last look here, we'll do tangent 15 degrees, just so we can get a glimpse of the tangent formula. And I'm just going to do tangent 45 degrees, subtract 30 degrees. Right? That's an easy way to get 15. And so I'm using a difference formula, so I'm going to use this guy right here. And we're going to get tangent 45, subtract tangent 30 divided by 1 plus tangent 45 tangent 30. And now it's time to start plugging in some ratios, all right? Tangent 45 is 1. Tangent 30 is root 3 over 3. Tangent 45, once again, is 1. And tangent 30 is, once again, root 3 divided by 3. Now, I don't like the complex fractions. I don't like seeing a denominator within a fraction. This is not good. So I'm going to go ahead and eliminate that immediately by multiplying the top and the bottom by the denominator of the fractions, which just happens to be a 3. So let's see what we get here. We're going to distribute, and we're going to get 3 times 1 is 3. The 3's cancel on the next fraction, 3 over 3. We're going to get root 3. And we're going to get over 3 plus the 3's cancel, root 3. So 3 subtract root 3 over 3 plus root 3. You'd love to say we're done. You really would. I would love to say we're done. But unfortunately, we got a minor issue, which is we have a radical in the denominator. So we're going to have to get that guy to go away. And we're going to use something you just used a lot in verifying to help us. I know that you've done this in Algebra 2 because your Algebra 2 teachers all basically pulled on you guys that you've learned this. So don't deny you've never seen it. But we're gonna use conjugates. The conjugate of the denominator is 3 subtract root 3. So we're going to multiply the top and the bottom of our fraction by 3 subtract root 3. And on the top, we're going to get what? A 9 subtract 3 root 3, subtract another 3 root 3, plus 3. I just distributed. Those are the 4 parts I got. A lot of people like to call that distribution FOIL to keep track of the parts. That's fine. The bottom of those, that's the beauty of conjugates. It's going to be difference of perfect squares, and you're going to get a first term of a 9, and you're going to get a last term of 3. Root 3 times root 3 is 3. But the middle terms, the positive and negative 3 root 3's cancel out. So what are we going to get here? 12. 9 plus 3 is 12. Subtract 6 root 3 all over 6. Well, guess what? I can factor a 6 out from the top. Just get a 2 subtract root 3. And so our answer on this problem, guys, is just going to be 2 subtract root 3. I know the algebra on the tangent problems is a little bit uglier, but it's more than you're more than capable of doing it. Nothing compared to some of the stuff you did in Algebra 2. You're fine, okay? Here's 2 quick problems. Why don't you pause this video for a second and try it on your own. I'm going to flash the answers, the worked out solutions for this in just a second. So why don't you go ahead and pause this right now and see how you do. Pause. No, I mean it. Pause. Thank you. Thanks for listening. Welcome back. Hopefully you tried these out, took a couple minutes and practiced. Here's the answers for you. Once again, go ahead and you can go ahead and pause this and kind of just look over how you did it. You could have used different angles on these, my friends, and gotten the same exact answers, okay? You didn't have to use the exact addition of angles that I used. You could have used different angles that added up to the same sums or even differences, and you should have still gotten the same answer. So go ahead and look through that work and see how you did, and please ask as many questions as you can. But that's what the assignment's going to be like for tonight. We're going to be working on page 199 out of the textbook. We're going to be doing problems 1 through 12. Try them. Show all your work. Do the best you can, and bring your questions to class. I hope this has been helpful. If not, a little bit chaotic. But welcome to Unit 4. Thanks for listening. Ba 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 ba.